talk about the fact that sometimes circuits get thought about as operating in a single frequency. You could imagine a circuit like we have over here with these L's and C's and R's. And if they operate in a very single frequency, in a very particular frequency, let's say in this case an omega 1 at 1 kilorad, then you'd say, okay, I can then try to just look at the elements in terms of their single resistance at that frequency. Maybe you'd call that impedance. Impedance is basically just the same thing as resistance, but with complex numbers. Okay, same thing. No need to create an extra term for it. And what you'd end up finding is that each of these inductors turn out to be an SL, right, or J omega L. And so it's J omega times that particular L. And this would give me 1 kilo ohm resistors times J. So they're imaginary resistances. And then the capacitance would give me something similar, and I'd say minus J times 1 kilo ohm. Now you might look at this and go, this is kind of interesting. What is the justification for actually doing this other than I can just put some numbers in and isn't that interesting? Well, there are certain circuits where things operate primarily around a single frequency. And that turns out to be really important. The obvious one that happens is typically in communication systems, because often what I'm doing is I'm taking a signal and I'm modulating it up to a higher frequency. So in those cases, for example, I have an input structure and then I'm modulating it, say, by a particular frequency, say a carrier F sub C. We're used to this all the time when we look at questions in communications. We're talking about communications like, in your cell phone, which is things like 900 megahertz, 2.4 gigahertz, and multiple other gigahertz standards. Which means I take a signal that has a frequency spectrum of like this, and then basically it gets modulated, which means that this action of modulation pushes the frequency responses in these two spaces. So it is a modulation of a signal, which pushes you into frequencies, and it does, and you get half the height in both cases. You can then, by doing the same another modulation, push it back down, or at least some part of it back down to baseband. But what's interesting is when I'm up at these higher frequencies, notice that I'm going to have the signals now going to be a tiny fraction. In fact, I've kind of exaggerated a bit, but it's really going to be a tiny fraction of that frequency. And so it's fair to say that if I have circuits that are, say, a power amplifier or an LNA driving something around particular frequencies, for all intents and purposes, the circuit is operating at nearly one frequency, so I can just kind of look at my circuit elements at that frequency and not worry about the other pieces. Another obvious place this shows up is where things are, again, operating by construction at a single frequency. Power. Power systems in the US is 60 hertz, in Europe it's 50 hertz, but it's a single frequency, and so you can just kind of talk about your elements as a single element. And this is one of the places where it historically started. But I would say both of these applications is where historically this kind of concept of having just a single impedance or a single resistance value shows up. And what that means is that your resistance stays the resistance, your capacitance becomes 1 over J omega 1, which is that frequency we're looking at, and the same times C, and the L is simply J omega 1 times L. This is what you're going to see often. And so it's important to be aware of it and use it. And there are times when this turns out to be very, very useful for analysis. And of course, you can take this particular circuit and say, say it's going to be right around the 1 kilorad per second range. And so then I could still just do KCL around V1 and write down what I get per particular equation. I get KCL at V out. Two different equations. This one here simplifies in an interesting way, just being that V1 is equal to V in plus V out. Very interesting circuit, actually, at that frequency. And this lower one, that V1 turns out to be V out times 1 plus J. The 1 kilo ohms all normalize out. And so as a result, I can then just solve and say, well, V out is then going to be equal to minus J times V in. This works out pretty well. And it gives you a lot of different possibilities and options of looking at things in a very specific frequency range when certain structures work out. And so it's kind of important just to have this, at your fingertips, and these are good ways to think about analyzing certain circuits at different times.